I welcome all the students present in this video lecture of applied thermodynamics, and the unit number is 6, fundamental of compressible fluid flow. In previous lecture we have start with the basics of the thermodynamic state relations, and we discuss about the basic types of the fluid flow. Then we have discussed about the basic thermodynamic relationship for the compressible flow. Then we have discussed about the certain different terms like the different types of specific heat, mechanical work, the relationship between the mechanical work and the heat supply using the first law of thermodynamics. Then we have discussed about the basics thermodynamic processes, that is constant pressure process, constant volume process, constant temperature process, adiabatic process, and polytropic process. Then after that we have discussed about the basic equation for one dimensional compressible flow, and that is the equation of state, continuity equation, momentum equation, and energy equation. So one by one we have derived that all the four equations. Today in this lecture we are going to discuss about the pressure wave propagations and the sound velocity. The disturbance in any solid, liquid, or gas is transmitted from one point to the another point, and this disturbance is created the pressure waves in the fluid, and that pressure waves moves with a velocity of sound in all the directions. So let us we consider over here one cylinder or one pipe. Let's say I'm considering one cylinder in which we have one piston. So this is the piston we have now. So just I'm giving the name that this is the first position, and the second positions will take at this point. So the distance between the first position and the second position, let we take as the distance traveled by the piston is x. Now the piston is moving with a speed of v. So let me write down all the things. So here let we assume that v, capital V, is a velocity of piston. Then suppose by applying this pressure, more pressures over here, as the piston is moving with a velocity v, so some disturbance created, let's say this is the disturbance waves which is created, and it is transmit with a certain velocity, and that velocity is called as a c. So here c is the velocity of the pressure waves, or we can say the sound waves, velocity of pressure wave, or we can called as a sound wave. Then we take the p is a pressure or fluid before the disturbance or the movement create. So p is the pressure before the movement of piston, and p plus dp is the pressure after the movement. So this is the fluid pressure after the disturbance. Then let we take the density, that rho is the density of a fluid before the movement of pistons. Rho plus d rho is the density after the compression of fluids. Let we take the time interval between the change in pressures. Then we consider the x is the distance traveled by the piston, or it is the distance between the first and second position of the piston. Then let me take the l. L is a distance traveled by the wave, pressure wave. So suppose this is the distance is traveled, and this distance is called as L minus x. Or we just have to write another expression over here, that velocity equals to the distance traveled divided by the time. So we have the expression that x equals to v into dt. Similarly, c is the velocity of the pressure wave which is traveled, and the pressure wave travel the distance L, so divided by dt. So we get L equals to the c into d. Now we have the continuity equations. So we apply the continuity equations. So it is the mass before the compression and mass of fluid after the compression. So now we know mass of the fluid before compression. So the density is rho, area of cylinder or the pipe is A, and length is L. so it is density into the volume, so we get the mass. And after compression, the density is rho plus d rho is there. Area is constant. Piston is travel from the 0 to the x distance. So the fluid is taking the only the length, that is L minus x. So here we get this expression. Now we just give the simplification. So rho a L equals to, previously we have this x equals to v dt and L equals to c dt. So we put it down the value over here in the bracket. So L equals to the c into dt, then this x equals to v into dt. Similarly here it is L also there, so we just write it is c dt. So rho a c into dt equals to rho plus d rho in the bracket a into c minus v into dt will be constant, or it is comes out of the bracket. So this dt is cancel it out. Similarly a is cancel it out. So finally we get the rho c equals to rho plus d rho in the bracket c minus v. Now we remove the bracket, so we get rho c minus rho v plus c into d rho minus v into d rho equals to rho c. Now rho c is cancel it out. This rho c is cancel it out, and we get the c into d rho equals to rho into v minus v into d rho. Now we know that d rho is very small quantity, so we neglect that terms compared to the c. So our final expression is c into d rho equals to, we get rho into v, because we neglect this term as d rho is very small. So this is we called as equation number 1. After applying the mass conservations, we are going for the momentum conservations. So we apply the conservations of momentum. So rate of change of momentum equals to the net force applied. So force applied, we know that force applied equals to the change in pressures. So pressures after the compression is P plus dp into A, and before, so it is P into A. So that is a change in the force. And change in momentum, so we know that m dot into v, so it is rho into v, so rho into v divided by dt into the change in velocity, so v minus 0. Initial velocity is 0 and final velocity becomes a v. So finally we get the rho a v divided by dt equals to, here we get the dp into a. So now a is cancelled out from both the terms, and we know that the volume equals to area into the length. Here it is L is there because this is volume, so area into length. So we get the rho L v divided by dt equals to dp. Now we know from the previous expression, students see here, this L equals to c into dt. So we just put down the value of L. So L equals to c dt. So our equation is becomes rho into c into dt into v divided by dt equals to dp. So this is the value of L. Now this dt is cancelled out, and we get the rho v equals to dp by c. So this is our second expression. So students, from previous expression, it is c d rho equals to rho v, and second equation is rho v equals to dp. So just I write the both the equations. So our first expression that we get, that c into d rho equals to rho into v, and second equation is rho v equals to dp upon c. So from these two expressions, we know that rho v is the same value. So we can write from the equation number 1, from equation number 1 and 2, we get c into d rho equals to dp divided by c. And finally, we can get the c to the power 2 equals to dp by d rho, so that we can write the c equals to the square root of dp by d rho. So this is our expressions of velocity of sound or the velocity of pressure wave propagations in the fluids. It is very important. Sometimes it is asked for the 7 marks in the GTU examinations, that derive the expression for the sound velocity or the pressure wave propagations velocity in a fluid medium. So we need to remember that c equals to the square root of dp by d rho. Now students, we are going to change this sound velocity that we receive from the previous expression, that c equals to the under root of dp by d rho in the terms of bulk modulus. Before going to convert this sound velocity in terms of bulk modulus, we just need to define the bulk modulus. The bulk modulus is indicated by k, and it has an expression that change in pressure divided by volumetric strain. So change in pressure means a dp, and volumetric strains means change in volume upon original volume. So this is called as a, and here we have one minus sign, and minus sign is indicating as you change the pressure, means pressure is increases, your volume is decreases, or if the expansion is there, so volume is increases, your pressure get decreases. So we get this minus sign over here. So our final expression is k equals to the minus dp divided by dv by v, or we can write that dv by v. Here we use this kind of sign for v, so we get minus dp by k. Now we also know that the compressibility, so compressibility is indicated by beta. Beta is called as a compressibilities, which is equals to the 1 upon bulk modulus. Now we again know the mass is conserved, so the conservation of mass is there. So mass conservations, so continuity equation, rho into v equals to constant. Now we do the differentiation, so rho into dv plus v into d rho equals to 0. Now we divide this expression by rho into v, so we get dv by v plus d rho by rho equals to 0, and from that we can write that minus dv by v equals to d rho by rho. So now we have the two expression. One is over here, this is one expression or expression number 1, and this is the expression number 2. We compare the value of this dv by v, so we get the dp by k equals to d rho by rho, and from this expression we know that dp by d rho equals to k by rho, and from this expression if we put it down the value of dp by d rho in over here, so we get the c equals to under root of k by rho, where k is a bulk modulus and rho is a density. So this is very important expression, that velocity of sound in terms of bulk modulus and density. Now students, we are going to derive the velocity of sound for isothermal processes. So we must need to remember that c equals to the under root of dp by d rho. This is very basic formula that we derive from the propagations of pressure wave. Now for the isothermal process, our expression is p divided by rho equals to constant. So we can write that p into rho to the power minus 1 equals to constant. Now we do the differentiation of this expression. So the p is constant. Here it becomes a minus 1 into rho to the power minus 2 into d rho plus rho to the power minus 1 into the dp equals to 0. Now we just give the simplification, so it becomes a minus p upon rho to the power 2 into the d rho plus 1 upon rho into the dp equals to 0. Now we multiplied both the terms by rho to the power 2, so it becomes a minus dp into rho plus rho into dp equals to 0. So from that we get p into d rho equals to rho into dp. So now we have the value p by rho equals to dp by d rho. So we just put down the value over here in this expression. So we get the velocity of sound for isothermal process, that is the square root of P by rho. And we can know that for the isothermal process, the K bulk modulus equals to the P for isothermal process. Now students, we are going for the derivations of velocity of sound expression for adiabatic processes. So again, just we need to remember the basic formula. Velocity of sound equals to under root of the dp by d rho. Now for adiabatic process, our basic expression is p by rho to the power gamma equals to constant. So we can rearrange that p into rho to the power minus gamma equals to constant. Now we do the differentiation again. So p is constant, rho to the power gamma, it becomes minus gamma into rho to the power minus gamma plus 1 into d rho plus rho to the power minus gamma as it is into dp equals to 0. The differentiation of constant is 0. Now we rearrange the terms. So here we get minus gamma p divided by into the rho, or we can write as rho to the power gamma into rho to the power minus 1 plus 1 upon rho to the power gamma into dp equals to 0. Here I'm writing down that d rho. So now finally we get minus gamma p into d rho plus rho into dp equals to 0. And if I'm rearranging the terms, so it becomes a gamma p into d rho equals to rho into dp. Now we make the subject dp by d rho. So we get the expressions that gamma p divided by rho. Now we know that p by rho equals to RT. So we just put down over here. So it becomes a gamma RT equals to dp by d rho. So now we put down the value of dp by d rho over here in this expression. So we get C equals to the under root of gamma RT. And this is the expressions of velocity of sound for adiabatic processes. Now, after discussion of this, all the three cases of velocity of sound, now we are going to define the Mach number and different flow regimes for compressible flow. So first of all, we define the Mach number. So Mach number is indicated by M, which is equals to the square root of the inertia force upon elastic force. So inertia force, we know that it is rho a into the v square, and the elastic force is bulk modulus into the k. So this is the square root. A is cancelled out from numerator and denominator sides, and we get v square divided by k by rho of square root. So finally we get v divided by square root of k by rho. We also know that our expression c equals to under root of k by rho. This is the velocity of sound in terms of bulk modulus and density. So now we put down the value. So our final expression for the Mach number is v divided by c. So we know that v is a velocity of fluid or the object moving in the fluids divided by c, that is the velocity of sound. So in this way we can able to define the Mach number. So Mach number is the ratio of velocity of a fluid to the velocity of sound in the fluids, and basis on the different value of this Mach number we can classify the different flow regimes for the compressible flow, and it is very important. So students, here basis on the Mach number value we can classify the different types of flow. So first, when the Mach number is less than 0.3, which indicates that the velocity of object is very less compared to the velocity of sound waves, and that kind of flow is called as a incompressible flow. So example of this is incompressible flow is a fan or blower or hydraulic. So flow generated by the fans, blowers that is called as a incompressible flow because the density cannot be changed. Now the second category, in which the Mach number is more than 0.3 but it is less than or 0.9. Here we can say that the velocity of object or the fluid is nearer to or less than the velocity of sound, and it is called as a subsonic flow. And the example is aircraft and turbo machineries. Then third classifications or the third regime of the flow is a 0.9 Mach number is lies in the range of 0.9 to the 1.1, and that is called as a transonic flow. And the examples are shock wave appears mixed in the subsonic and sonic flow, like the compressor blades. Then the fourth one, when your Mach number is having the exactly value of 1, which implies that the velocity of object and velocity of sounds are equal, and that kind of flow is called as a sonic flow. And the fifth one, that where the Mach number is greater than of 1, which indicate that the velocity of object is greater than of velocity of sound, and that is called as a supersonic. And last one is when your Mach number is greater than 7, means your velocity of object is very high compared to the velocity of sound. That kind of flow is called as a hypersonic flow. So this is the examples of different flow regimes for the compressible. So students, this is the end from my side. Thank you for attending this lecture. Thank you all.